So welcome everyone to this month's First Friday's online acoustics seminar. And it's been 16 years since the Strad3D project. And I remember vividly hand carrying two of those instruments down to South Carolina. And this is a project that Professor George Bissinger and Sam Zygmuntowicz organized to do acoustic measurements on three Kreutzers instruments using, at that time, the state-of-the-art 3D laser scanners. So I'm going to turn it over to you, Sam, and to talk about this project and, what are your thoughts 16 years later?
Well, thank you very much. Well, for one thing, I want to thank the VSA. We recently, the experiments were 2006, hard to believe, and the Strad3D DVD was released in 2009. And I had a friend who was a digital designer and did a beautiful design with a lot of interactive features, all done in Flash, which after a few years stopped working. So this project has been basically dormant for a long time, which seemed a pity to me. And if nothing else, it is a huge archive of really, I think, useful information. So I recently was contacted by Adrian Lopez, I don't know if he's on today, who, for his own use, started to recode Strad3D to make the interactives work again. And I said, that's really cool. Could you do more of that? And he did. He did a beautiful job. All the project is fully functional now. And I decided that at this point it should just belong to everyone. And it's up on the web now. Anyone who is interested can find it at www.strad3d.org. Strad3d.org. All the information is there. It's free. So it was available. So the question, what's it good for and what's it about? So my talk today, there's a lot of pieces that I'm going to draw from. Just to give you a rough overview of the shape of the talk and try to keep myself on track, is I want to start by just introducing the changes in the field of violin acoustics as far as it relates to violin makers during the time I've been involved with it, starting with some of the early Titans and the increasing sophistication of some of the research on the one hand, the greater availability of information to the violin making community on the other hand, and the increased cooperation between some of the top scientists and violin makers, the democratization of the technology involved to the point where a lot of violin makers can use similar techniques to scientists that would have only been available in massive labs before. So that's that, and then I'm going to just sort of then explore Strad3D, the actual project online. One comment I've gotten from a lot of people when I've given presentations is I'll show something and they'll say, I had no idea that was in there. It's kind of a very sprawling project, and there's a lot of what I consider interesting bits and hidden treasures that are not so obvious. So we'll go through those a little bit. The final section of the talk, if I get to that far, would be how in my own work and with my collaborators here, I've tried to take the current ideas that I drew from this research and apply them in a more informal but still not totally ad hoc way in my own work. I will say one thing at the top. I did contact George Bissinger. I should have gotten to him earlier. And if he was here, this would be a very different talk because, and I'll talk about that in a minute, but there's some very fine scientific papers that are online in the project. I will not try to discuss those papers in depth. I'm totally not qualified to do that. And I don't want to misrepresent them. I may quote from what I think are key ideas, but I recommend that anyone who's able to and is interested go directly to the project. There's an article archive with a number of articles from Dr. Bissinger. So I'm going to be talking about this more from a personal perspective and as a violin maker. So that's my preamble. First, I'm just going to start with a little more, how do I get out of this? A little more chaos. I found an old presentation I'd given about 10 years ago called 10 Years of Acoustic Tinkering, and I realized time is flying. But the questions are still kind of the same. It's like, what are we trying to accomplish and where is it going? So I'm just going to talk a little bit about my own journey in violin acoustics, which I think just sort of parallels everybody else's journey who's here. This is Norman Pickering, who for many of us was really the bridge to acoustics. He was very active in the VSA for many, many years. He's was a brilliant engineer, many, many patents. He was most famous for inventing the first commercially viable stereo phono cartridge, the Pickering cartridge. It was a very big deal at the time. At the age of 50, he got involved in violin acoustics, thinking it would be a little detour, and he lived to be 99 and was still working on it. He's an engineer rather than a physicist. He introduced, as I say, many of us to trying to look at things more analytically. And I would also just say, that I place a lot of these things in what I consider to be the post-Carleen Hutchins period. That was Carleen and Saunders, and many of those people are a little bit before my time. And there was a lot of emphasis on plate tuning. Norman, I think, was as an engineer, was spent a lot of time on what I think what we'd call systems analysis and how does the finish instrument work. That is the Norman Pickering acoustic testing rig, which was the first one that I saw, and it was set upstairs at the violin making workshop. There was often one in the conference room, and the violin makers would go up there. I don't have a clock, so I should probably see, not dawdle too much. A lot of violin makers would bring their violins up to be tested and get the results printed out and come out of the room with a bunch of squiggly lines, wondering what it all meant. And that was pretty much in the same place for me until basically Norman at one point gave me a Trojan horse of a present, which was the use of one of his acoustic rigs. It uses a transducer that he handmade, which basically is similar to what they use to cut vinyl records. So you play your violin, it's like a record in reverse. You put the signal in with the transducer in through the bridge. There's a lot to say about it, but once I had it in my own hands, I realized I could track before and after, compare instruments, and it was very different than relying on just getting a readout. The next step of all that was not just, well, I'll just go back to Norman for a second. One of the things he also did is he had a little ball, a metal ball on a spring that you could hold like a little mallet. But then you could put a signal into your violin and then probe around the surface, and when there was an area that was vibrating, it would rattle the ball. And it was a very, very, very analog form of modal analysis. And that was trying to link what was coming out of the violin with the way the violin was moving. And Oliver Rodgers was very, I then met him, another engineer, involved with the Acoustic Society, Cat Acoustics Society for very long time, and he was always trying to make equipment that was very accessible to violin makers. There's a picture of him with his modal sniffing rig, which is a little basically a speaker without a cone that vibrates with a little stylus. It could be a plastic drinking straw that touches the bridge of the violin, and you could put a signal in with a signal generator and then use a tiny microphone with an oscilloscope and see where it was vibrating. And these were very accessible tools that any violin maker could use. And then I began to think, how would I connect this to my own experience as a violin restorer and a violin maker? Now, one thing with old violins, which we all know, is that they're very often very altered. You know, there's a lot of work is done to them. This is the interior of a Stradivari, and you know, people repair them because they break, but then they're reinforcing them, which must change the sound. Restorers do know that you can also change the sound by deliberately putting in reinforcements. Here's a violin of mine that I reinforced, and it sort of works, but it's very like, well, let's just try this. And I wanted a way that would be more controlled, and you could actually calculate where things went. This is the Gluey project, which some of you have heard of, kind of rigged up in one of its incarnations. And one of the things about this, you know, you could put things on with hot melt adhesive very quickly, and you could make very rapid modifications, and you could hear them really quickly. You could make the modifications, play before, change something, play it afterwards and say, is that good or bad? And you could hear it right away. And if you thought, that's good, then you could test it. These were made with the Joseph Curtin rig, Joseph testing it at various stages. Here are two spectra of Gluey. Okay, thank you. Right, the red is before and the blue is afterwards. This is like with probably a gram or gram and a half of little studs stuck to the violin, a very minimal amount. And you actually can see the violin went from sounding kind of very woofy and not very appealing to being actually quite convincingly good in, like, you know, you could do that in 20 minutes, and it was quite a revelation to know how much you could change an instrument. But how could you change it, and where, and how did you figure it out? Basically, I was doing this by hunt and peck. So the question is, can you do more than hunt and peck? And someone else who I met through the acoustics workshop at this point was Dr. George Bissinger, who is, was the leading American violin acoustics researcher, worked closely with Carlene, had a full anechoic chamber at he was at East Carolina University. He had an anechoic chamber to do very good acoustic testing. He also did laser scanning to do modal analysis using a simple, it wasn't simple, but by a program called Star. He would make his own animations. Amazing stuff. And he studied many violins there, but he never really had any great violins there. So at one point, he worked with a company called Polytech, which makes scanning lasers. And he had one scanning laser, which does what we call, I guess you can make a two-dimensional scan. You basically scan a violin at a bunch of points, and then you can make a two-dimensional animation out of it. Polytech offered him the state-of-the-art three-dimensional laser scanning array, which they would send to his lab with a team of technicians. But they needed to have a Strad so that they could tell their board of directors, we're going to go scan a Strad. So that's where I got involved in this. Originally, just in a very utilitarian way, as the Strad wrangler, you know, to locate the Strads and make sure no one broke them. And this led us into Strad3D. This was a massive undertaking, which Fan was very intimately involved with. I actually managed to find, well, I'll tell more details later. I think at this point, maybe I'll switch over to the actual Strad3D interface. Is everyone hearing me all right? Am I connected and all that?
Yep.
Okay, good. Okay. Well, we'll just start here. Okay. We were going to go down to, I was able to locate 3 violins, the Titian Strad, the Wilmot Strad, and the Plowden Guarneri, which were all just amazing, really the best of their types. A great golden period Strad in wonderful condition, a great late period Strad, and one of the finest Del Jesus. this was actually, I was kind of a tag-along, to be honest, but this was a dream of mine to actually be able to, I always wanted to be able to see what I was working on. I'll just skim through some of these pictures. This is George setting up the Titian on, this is the apparatus with which he suspended it. He had an automated impulse tapper, we like to call it. We don't really like to use the word impact hammer. We also did CT scans. These are 3 violins going through the CT scanner in a very clever
maybe
Sorry, what's that?
I think somebody.
No,
okay. All right. So, when George started out, I think he may have been one of the first people to do CT scanning of violins, and it was very expensive and difficult to get access to a scanner. So to do multiple instruments, he stacked them up just to get more through at one point. But it actually made a great graphic afterwards, even though it's not as hard to get a scanner now. So this is what I call a Cremona sandwich going through the scanner. This is David Oliver, who was not sure of his title. I think he was a chief technology officer at Polytech. This is Vikrant Pelin, who was a senior technician. And there was one other guy from Polytech. George in the lab with, looks like the Wilmot. Yes. This is the Titian on the rack. First to set it up, these little spots, they first probe around, they create the 3D model and the scanning pattern first. And then when it's all set up, the 3 lasers will basically in an automated way scan the whole instrument. Let's see, I'm just going to scoop ahead a little bit. Well, okay, I'll just go through.
Sam, can I just make a point of clarification, because the yes. 3D scanning in this particular case, it's actually it records the vibrations of the instrument, but traditional laser scanning vibrometers only record the movement in one direction, and so the power of the 3D scanners with 3 lasers is that it's able to record the movement of the plate vibrations in all 3 dimensions.
Exactly. Yeah. Right. So George had a single point scanner. You see here the 3 laser scanners. Basically, each of these shoots a beam of light at the violin surface, but they're offset from each other a certain amount. So one is programmed to record the motion, the out of plane motion towards and away from they're not cameras, the scanner. And the other one is meant to record the motion side to side, and another one up and down. They have to create, let's see if I have it here. From these scan points, which are linked together in trapezoids, they create a 3D model of the instrument. And they record basically the spectra at each of these points. The software can then animate that 3D model, and it can do it frequency by frequency. So first, there's the scanner, there's the model. This is a video monitoring of it. I think I'll just jump ahead and just go right to the 3D scans themselves, which to me, I never get tired of looking at these. I hope you don't either. This is a video montage I put together of this stuff. I've put a little marker at the Soundpost position. A0, CBR. I'll pause for 1 second. This image is a little crude because we couldn't scan under the fingerboard, and because the lasers were converging from different positions, there was basically an area around the fingerboard that we couldn't get close to. So there's a big cutout there. Same thing for the tailpiece. If we had this to do over again, I'm sure we could set this up in a more sophisticated way, but it wasn't intended to be so, but for me anyway, it's turned out to be a once-in-a-lifetime opportunity, so hopefully it won't stay that way. B1 minus. B1 plus.
B1 plus.
Into the not so well named modes. One thing that is amazing about the lasers at that time, it's fairly easy to track what the people call the signature modes, A0, CBR, B1 minus, B1 plus. Most violins behave very similarly. You know where to look for them. So because you know where to look for them, you can find them. High frequencies were very elusive and hard to categorize. One of the things the laser is capable of doing is capturing, really as high as you can go. It's a non-contact way of scanning. So the other thing that's I find fun is that things that we heard described, Norman described this years ago, and the reason I put that that marker on there is, it was pretty well described that at lower frequencies, at the signature modes, the first of them, the Soundpost is almost a steady point, and the bass bar is moving quite a bit, which you can see here. Very clearly, and this is really happening. This is not made up. These are not actually processed. But then as you get higher, like right here, you're getting kind of just a pumping whole surface. And then you get waving, and that the wings start to get activated. And as you get higher and higher, the motions get, I would say, at low frequencies, you could kind of imagine the violin doing the things it does. At high frequencies, it's like Joe Reg was was on the testing sessions, and he said, we all knew the violin vibrated, but we didn't know it looked like a belly dancer. The wings are getting very active. And you'll notice more different parts of the instrument are getting activated. Better move it along. Okay, I'm going to skip ahead a little bit to where it gets really weird. Okay, all these things are available on the web, so you can look at these at your leisure. I'm probably going to move on now. That is like the core of it, and this is in a way where Dr. Bissinger's interests and my interests kind of diverged. There was a great deal of data that was drawn out of this, and there's also these awesome images. And as a very visual person, I think I just wanted to look at the pictures and dream. And Dr. Bissinger wanted to get data and actually say something, write serious papers. I think you can see our difference in perspective. I'm going to go for a second to the research archive. These are, sorry? Okay. These are Dr. Bissinger's papers. And this one, Structural Acoustics of Good and Bad Violins, focuses on the Strad3D work and also on his many, many years. He had a project called VIOCADEAS. However, I'm not sure if I'm pronouncing it right. Violin computer-aided analysis, basically. And it's very interesting that it's the study of good and bad violins. Just studying good violins by themselves doesn't tell you as much unless you can contrast them with something. If I won't, well, actually, let's just go to his paper for a second. And if I dare, I might quote from his abstract. I'm not going to talk about his paper. It's really worth reading. Let's see. Okay, this was interesting. Basically, what he was looking at is how much energy and how the energy goes into the violin and how it is used and how it comes out. I think in lectures I heard him, I hope I'm using this correctly, Fan, feel free to jump in. His analogy was a leaky bucket, that you pour water energy into the violin and it leaks out in various places. It can leak out as sound, which he would call radiation damping, audible sound, motions of the surface that effectively move air which create vibration, which our ears can hear. There is internal damping, which is, I think viscous damping is another way to describe it, which is energy that is absorbed in friction or in vibrations that do not produce sound. And then there's fixture damping, which is, in his case, there's a holder for the violin, and that absorbs some energy. When a violin is actually used by a real human being, the human is a huge fixture and damps the violin incredibly. So part of what he was trying to do was track, where the energy went. And he did say that that comparing the good violins, the great violins with the bad violins, he said, well, generally it showed no robust bad excellent differentiators with one significant exception. A0 near 280 was the only strongly radiating resonance in the violin's lowest octave, was stronger in the excellent than in the bad violins, and the good violins were in the middle. Radiation and total damping is the radiation, internal and fixture. Radiation is the portion that makes sound we hear. Of the two old Italian violins appeared slightly higher than for those bad violins because of their lower critical feature, frequency, and slightly lower mass. That's as much as I'm going to say about it. Anyone who can should read those articles. And then I'll just talk my own articles. I'm not going to go them all, but there's actually at this point, I looked back on it and I take them as a whole, and it is sort of summarizes the work that I've done with this. The first was when we first did the work. And it's just saying, well, how do we use this stuff? And there's the violins going through the scanner. How cool is that? These technological resources now available offer the chance to tease out some of the violin's hidden functions. These are just some still shots. I still think this stuff is just so awesome, I have to confess. CT scans, which have proven really useful. You can get density information off of old instruments in a non-destructive or invasive way, the violin maker's perspective. Spectra. So this was, this came out, I think, in 2000. When was this? I don't even know. 2009. This came out at the time that we were releasing Strad3D. Not consequently, but later, actually it was the same year, the Strad magazine often features posters of instruments which violin makers enjoy. They're basically like blueprints, and usually an article that accompanies it. I did one of the Titian, and it was the first of those Strad articles. I basically made the poster an article that I would have wanted to read, which included all the usual measurements and photos, but also the arches were taken from the CT scans directly instead of from drawings. And it discussed the acoustics a little bit, and it drew on the resources of Strad3D. And one of the things about Strad3D, the scientific part of it was entirely Dr. Bissinger. But I would say my vision of it was that stuff was amazing and the imagery was amazing, but there was, that belonged to the scientific world. And then we have the knowledge that belongs to the violin making world. And the two worlds don't tend to meet very often. And what if you could put those two worldviews together and that imagery together? You would have the most complete view of a violin possible. That included François Denis recreating the proportional designs. It included the modal analysis that Dr. Bissinger did. And then my own photography from Tucker Densley. We did dendrochronology. Anyway, I thought this was a step forward for violin maker expertise and a 3D view of the violin, if you will. How are we doing on time? Good.
Take as long as you want, Sam.
Okay. Well, having done the Titian, the Plowden was next. And I gave that the same treatment. Now, I mean, so a lot of this stuff is just like, you know, violin makers like this kind of stuff. The knife marks on the linings of the inside of the Plowden, the tooth plane marks, the roughness of the block. You know, that's the nitty gritty from which the violin is made, and details of carving. But then also to be able to see in detail what was going on with that violin. I mean, there's a lot of things that, even if you saw this in numbers, it wouldn't make the same impression. You know, like, for example, I'm used to thinking of this as being the thickest area of a violin, and it often is, but in this case, there was a bit of a flat spot there. They're just, you know, and I will say, just for disclaimers, that anything that I say that is not a quote from Dr. Bissinger, you can consider speculation and take it as you will. Because, you know, scientists, they have to write accurately about good data. But not being a scientist, my challenge is to see if I can draw conclusions from not so great data. But I mean, there are people who talk about scraping violins from the outside to alter the tone. Well, this might support that. I mean, the Curtin side is nice, and maybe, who knows? There it is to see. And then it also has what I always thought was important, which you didn't used to see in violin expertise so much, was a serious effort to have a subjective, accurately subjective, is there such a thing? A sincerely subjective description of sound. And then try to tie that to structure. So, you know, and then I was able to draw from, for example, what we have here is the purple is the, how do you make that bigger? Just Command plus. The purple is the Plowden. The green is the Titian. These spectra, by the way, were taken by Joseph Curtin. They are not from Dr. Bissinger's data, which I would have preferred, but I don't know how to process his data. But it is sort of what you would expect comparing Strad to Del Jesu, which is that the Guarneri has a very big A0 and the B1 minus is higher. So the Plowden has a very boomy and warm sound. And then a little less in what some people call the transition hill and I call the projection region. And then starting at, this is for the Strad, and then starting at where we consider the bridge hill to begin somewhere in 1800 or something, the Strad rides proud. So the Titian is a very strong, very assertive violin, and the Plowden is a very velvety violin, and you kind of can see it. And that is really the basis of all the work we're doing. We have to, it's sort of like the credo, what we believe if we're studying acoustics is that sound is caused by vibration, vibration is caused by structure, and the structure is what we make or alter, and we could understand it if we just tried it long enough. And then the other thing I started to include in this is a little ghettoized, if you will, box of acoustic stuff. Not everyone's into it, so I tried to keep it separate. The stuff in here is quoting from people, and it's real numbers. Now, I had the tap tones of the Plowden that happened to be open in my shop once. Some quotes from Dr. Bissinger, where he stated, the Plowden possessed the strongest low end, the lowest critical frequency of any violin tested, and a somewhat more extended high end, somewhat contradictory properties, in that it had both full bass and extended high frequencies. Anyway, I did the same for the Wilmot. We'll come to that in a minute. Let's just go back to the, all this stuff is here. I'll just go, show you some of my favorite things. Well, the photos, just there's nice photos, and you can zoom in. It's just a nice resource, and they're also downloadable. You can look at the measurements of the fiddles. You can look at the CT scans of the arches. Basically, the concept for the interface was to be able to jump back and forth to different methods of inquiry. So the logic here is that this is what it looks like. This is what it measures. This is what cross sections we can't usually see are. This is what it sounds like. Okay, now people often talk about sound tests, and there's been amazing work by Claudia and Joseph and Van, people are often not as good at hearing sound as they think, and it's often thought that it's pretty hard to hear the distinctions between violins. But I'm going to play you something quickly. Okay, this is, I don't even know what's coming through over Zoom. You could do this on your own time, but it takes one note for, I think, almost anybody who has any ear at all to hear the difference between the Plowden and the Wilmot. It doesn't take a lot of listening. So to me, it's a lot simpler than people sometimes make it. So this is what it sounds like. Well, what is the nature of sound? And so we put in the spectra of the instruments. There's the Plowden compared to the Wilmot. The Plowden, once again, has higher low frequencies than the Strad, late Strad. The Strad at this time had a markedly higher, sorry, I'm just sitting here by. So it's you can see it very visually. It's not mysterious, or it's not excessively mysterious. This viewer, you can, if you prefer, you can look at it in 1/9 of an octave or 1/3 of an octave. Now, there is a principle that every frequency on the violin, let's go back to the detail, like, the B1 plus, every little spike here is caused by one specific type of motion of the violin, which is called a mode. And every violin will be different, and it will vibrate in patterns according to its nature, its material properties, its shape, its thickness. So then we come to modal analysis. George Stepani. George, are you here?
He should be.
Okay.
Yeah, I'm here.
Okay. Well, George was a great collaborator as we were putting this together and contributed some wonderful things to the project. And I hope you'll correct me when I misrepresent your ideas. This was a slideshow that George put together. One of the things conceptually about this project, Dr. Bissinger quite rightly writes papers that are peer-reviewed and appear in academic journals. One thing is, I guess, I don't know if you want to call it a courtesy, is I did not include any of my own speculations in, or very few, in the project. I tried to keep it really a presentation of all the different data. But I also thought this project had not only a scientific aspect, but a consciousness-raising aspect. And that for violin makers, they were going to take it in as a whole. And for me, it changed the way I saw the violin. And I thought it would do that for others. This can also be used as a textbook. You could go through these categories and you could teach, I think, a fairly complete course on violin acoustics and violin making while you're at it from the materials in here. What we have here, this is shapes of the signature modes. What we see here is the Titian Strad in a Spectra. I think you all know about Spectra. The up and down is amplitude. From left to right is frequency. So this is a spectra of the G note being played with a bow on the Titian, and it has the fundamental, all the harmonics in order. There's many interesting things about it, including that the fundamental is one of the lowest frequencies. So well, this is a nice little graphic I always enjoyed, which is many different modes superimposed on each other. So this is the spectra of the Jackson Strad, for example. And it shows that, it doesn't necessarily line up with any particular frequencies on any particular note. There's what people call the signature modes, and that's what we're going to look at here. I think this is all very basic to most of you, but it's a good little primer, and I quite like the graphics here. So that is the A0. These are taken with George Stepani's modal analysis software. One of the big stories to all of this is, the Polytech scanner was, I think at the time, was $750,000 or more for the 3 scanners, not to mention the expertise and the personnel to operate it, which is nothing that I'm ever going to have or do. So George Stepani's software could work with a laptop and an accelerometer and an impact hammer. It would have been inconceivable that these kind of animations could be made outside of a lab some years ago. There are some nice demos of trying to simplify these are hand-drawn, I believe. And then one thing that, one of the things is, how do you tease more information out of what's there? You see the motion, but something that George was able to calculate as well is where it bends the most. So for example, here's CBR, and you can see the motion. The motion is showing you the basic way, and this is real. These are not simulations. Is that correct, George? Yeah.
It's a mathematical post-processing of measured data, but it is based on actual measurements. It's not fantasy.
Right. Yeah. Thank you. And so the colors are additional processing, which is locating not just where the maximum motion is, but where the maximum bending is. Now, it's arguable, but quite plausible, that where a plate bends is more important for modifying it than where it moves the most. He also had this is the same motion with a long grain bending, and this is with a twist. And you keep them all going and try to keep focus on all of them. It'll just blow your mind. So these are breathing modes. I'm not going to go through every picture here. This is all online. And it's all been recoded, so it's working again. B1 minus. These are all worth looking at in detail. Now, we also have other modal videos. One of the things that Dr. Bissinger provided from another project was air animations. These are done with basically microphones. It's called near-field holography. I'm not going to try to explain it. There is an explanatory paper in Dr. Bissinger's articles. This combines modal animation with animation of the air coming out. This is the A0. You see the air coming out evenly, pumping in and out of the instrument. CBR is quite interesting because it's a twisting mode. It's very active, but because it's sort of symmetrical, air is coming in at one F-hole and out of the other. That's why it doesn't project. It's because one is pulling, one's sucking, one's blowing. Very little net change in volume once you step away from the violin. Then when you get to the B1, the Bs, then the motion gets efficient again. So what we also have here is, let's see. These are, let's see, this is the Jackson Strad, for example. One of the problems, and one of the things that I have found that I've tried to do, and that George has done a lot and assisted a lot with, is trying to simplify complex information into more assimilatable bits of information. And to me, it's like one of the, my little rule of thumb corollary is that the data, the quality and the detail of the data should be proportional to what you can do about it. If there's super detail and it's nothing that you can influence, then it's just confusing. And if so, what we have here is bands. In this case, they're in 10 hertz bands. So instead of trying to extract single modes, in an automated way, his software produced these band averages, all the motion within that 10 hertz range. And it happens that at the signature modes, it's pretty good at capturing individual modes as well. When you get to the higher modes, you know, those are much trickier. But as we scan ahead, the shapes become much less what you'd expect. But so, and there you can start looking at the high modes statistically instead of, you know, that you're more likely to have more of this band of high modes right over here. This was recently recoded by Adrian, and it's actually, I think, great. You can actually pick, for example, you could pick any of these and just scan around, probably more than you even want to. But you know, this is a little, what would I say, less sexy looking than the 3D animations, which we produced a movie of with sound effects. But there is a ton of data here, including what I think was a, you know, just another view of the signature modes. There's CBR, very symmetrical. There's probably B1 minus with the baseball animations, as they call them. There's B1 plus, more or less what you'd expect. And then as we get, there's some of these pumping things as we get into the 700s. And then as we get into the transition hill, you start to get a lot of motion on the F-holes. Like there's a lot where you can really see the center is flexing. And then as you go up more, another flex, and then sometimes just one F-hole going, then the other one. Then as you get higher, you get other areas going, and then when you get into the highest regions, I'm going to skip ahead. This is what we're looking at is 200 to 2,000. We're going to take the same fiddle and go 1,000 to 3,500. We no longer have phase now because it's too hard to pin down. So right now, it's kind of interesting. Sometimes you look at this, you almost feel like you're looking at a picture of the arch because the modes follow the arches so well. And then here we are in the transition region, and we're going into what I like to call the Dunval ditch, where there's often a little bit of a dip. And then as we get higher, now the F-holes are no longer the most active areas. And it's moved to areas which you would not have necessarily thought were active, which is something that I was discovering with Gluey and also with Oliver Rodgers coaching, is that there are little parts of the violin that you would just never think do anything, and they're incredibly sensitive. And we just can't see it, and we don't think to look there. So all of this is super interesting to me. And also what's unusual about this is normally we have no way to study the high modes. And a lot more of that could be done. But in this case, I think there's, you know, this is an incredible resource. I think this section, very few people who have Strad3D, I think, have looked at this, and I think it's a lost treasure. The CT scans are sort of self-explanatory. They're really cool. One of my favorites is just the three violins, because it's a very satisfying graphic. But once you get into the violins themselves, I believe that's the, well, let's see, we should be able to tell pretty easily. Looks, can I tell? I'm going to say that's the Wilmot on the top, the Plowden in the middle. Well, the Wilmot at my right, the Plowden in the middle, and the Titian. I mean, one thing that's really some things that jump out when you look at this stuff is, let's go down a little more, is, we're comparing these violins, but one of the real obvious things is that the Titian has a kind of a really massive bass bar. Where's the highest point? Oh, that's good enough. The Plowden has a really tiny bass bar, and the Wilmot is pretty small as well. So part of what we're hearing is not just the fiddles themselves, but the way they're set up. And you can't separate one from the other, truly. Anyway, so those are the CT scans, worth more of a look. Research and articles, I think I have shown you. I will jump ahead to the last paper, and I now think of the articles I wrote they've been done years apart, many years apart, but there's sort of a continuum, starting with an overview of like an introduction to all this technology, then using it to analyze the Titian from a violin maker's point of view, and then the Plowden, and then the Wilmot. Most recently, I wrote an article that I wouldn't have included in Strad3D originally, which is like, well, there's the question. If someone makes an exact copy of a Stradivari, will it sound like a Stradivari? Also, it's like, a lot of times people have asked me, okay, all this stuff you're doing with acoustics, it's cool, but does this help you make a better violin? And I find that it's an embarrassingly long answer to that question, and people lose interest before I come to any conclusion. So to me, this was a question to myself. Does this acoustic analysis deepen our understanding in a useful way? Can new violins capture the characteristics of old instruments? Those are the two questions. And so one of the things, since I had this huge body of information, all my measurements and photos and CT scans, plus the acoustic information and the spectra, and what could you do with all that? If you can't make something with all that information, what's the point of having that much information? This article was published. It's also included in the Strad3D now. You can read it there. One thing I tried to do, my method here was to summarize some of the physical attributes, my own impression, and then I also, to the extent I asked Cholang Lin to describe what he thinks the characteristics of the Titian are tonally. So I can't find that section, but like, for example, Jimmy said it's resistant in all registers. Kavakos, I had a quote from Kavakos, who knows where it is here. Is it further ahead? Let's see. I'm sorry, give me a moment here.
Otherwise, you can use just Control F
Search.
and search for
Anyway, it's I feel like I'm having aphasia. I just can't see it. The point is, let's see, is that I wanted to start with a subjective description, and to the extent possible, I had interviewed, Kavakos had described his own violin.
Sam, Kavakos' comments is on page 46.
Oh, thank you. Skip ahead a little bit.
There we go.
Okay, great. Thank you. I will admit, he had a longer section. I extracted the part that I thought was most cogent, which I'm sure reflects my own prejudices. But so he said, the Wilmot is a very robust, powerful instrument. It has a refined, perfumed kind of tone quality under the ear. Yet when I hear somebody else play it in a concert hall, it is an incredibly complex, multidimensional character. So what does he mean by that? And then the rest of it is my interpretation. which is this combination of complex yet robust and carrying may seem paradoxical. And then I basically said, what could that mean in terms of the Wilmot's spectra? And I said the Wilmot has a very distinctive spectra in that it is not very boomy on the lower range. It's quite reduced in the transition region, and then it has a high bridge hill area. And I posit, this is my opinion now, I find that stronger mid-range output enhances the sensation of presence or edge under the ear. So this reduced mid-range might well give a more refined impression to the player. Sholang Lin, by contrast, writes, I would describe, some of these words, it's hard to know what they mean. I would describe the Titian sound as aristocratic with a really ringing upper register and a rich, full G string. Throughout the range of the violin, there is an incredible core of sound that is both powerful and nuanced. What does that mean? That's what my eye was drawn to that. And in fact, the spectra of the Titian is pretty filled in. It doesn't have as many high dips. It doesn't have a real dip in the transition hill as much. I think that is probably consistent with his description of being even and powerful across the spectra. I used my own description of the Plowden, so it's, this is my opinion. The tone is smooth and velvety with a touch of reediness that gives presence to the sound. That's what I said in 2000 and whatever when I was writing the article about it. When I look at the spectra of the Titian, we can go to the spectra of those instruments, but why don't we do that? Do I have them separately? Yeah, well, these are 1/3 of an octave smoothings of the spectra of those three violins. Is that appearing to you? So the Plowden, full with a touch of, so here, I'm going to be a bouncing ball. Full with a touch of reediness that gives presence to the sound. Let's do the Wilmot. Refined and perfumey, yet robust and carrying in a hull. The Titian, focused across its spectra.
Aristocratic.
I don't know where aristocratic really lies, but one part of my effort in this article was, I think it was, I don't know if I'm misquoting, Albert Einstein or someone said, everything should be made as simple as possible, but not simpler. But I hope I haven't made it too simple, but I was trying to say, what are the fewest adjectives that could describe the sound adequately? And what are the fewest features of the spectra that could describe the instrument as well? So I really only focused on the areas where you tend to find peaks. I did not focus on the dips. So basically, in this very reduced vision, there's a low frequency, there's a mid frequency, and a high frequency. And that's all I was discussing. Now so then I made my 3 copies. I think the most obvious difference between these instruments is in the arching. Fan, how long will I be able to go with this?
Go as long as you want.
Okay. Hope people are with me here. I made the copies just because, I thought, well, why not? And first of all, I can't keep the Titian in my shop, and having studied it for so long, and same thing with the Plowden, they're sort of touchstones. It was fun to actually make real copies of them because, like I say, when am I going to have that much data and that opportunity? So here's the copies. Also in 1/3 of an octave. And they're not exactly the same, but if you will, here's the Plowden. Here's a fullness that makes it velvety and something that gives it a, what did I call it?
Reedy?
Reedy quality. One thing is that I think my copy is a little higher in the bridge hill and maybe a little more output altogether. Although, for a caveat, my calibration, I do the best I can, but I always take my calibration and my test with a grain of salt. My own fiddles were all tested, fairly close together, so these should be well calibrated to each other. The Wilmot, well, actually, it was a little fuller than the original, but it did actually have this reduced mid-range quite markedly, and then a pretty strong bridge hill. And the Titian, I would say, I had more of a Dunval ditch than the real Titian, so maybe not quite as robust all across the range. Let's compare the new fiddles to the old fiddles. So what you have in these images is I'm fueling myself with bubble tea while I talk. Is Spectra taken here of the black is my fiddle, the red is the real Plowden. And this was after, this was not from Strad3D at this point. This was from after both the Plowden and the Wilmot were subsequently restored, and I did test them again. They changed quite a bit. So comparing my fiddle in black to the Del Jason, once again, this is a just only slightly smooth Spectra, superimposed with third of an octave, just so you can see trend lines. I would maintain that the trend line is not entirely dissimilar. Is that enough caveats? It's not identical, but it kind of like goes up at the transition hill and goes up at the low range. I would say mine is a little more brilliant, but related-ish. There's the Titian, and I guess I would say the same thing. I think with the biggest difference I would say is, well, differences that are obvious is that in this mid-range, I'm quite a bit lower than the Titian, and then I fall off in the high range quicker than the Titian. So I'd probably guess that as far as that resilient focus across the range, I'll bet the Titian's still beating my copy here. But, you know, it's up to you to decide, is it actually similar enough to say that it is following the trend? And on the Wilmot, I think is pretty successful. I mean, in a certain way, the copy is fuller in the low range, which might be a good thing. But it sort of follows the lowered transition presence region. And the Wilmot, once again, has a very shimmery high end. So I wouldn't say that I'm beating these fiddles. I don't really know. I didn't get to hear them back to back. But if I may, and people could dispute it, I would say it's, when we come to the conclusions, we had three questions. Does acoustic analysis help us understand violin function in a useful way? So to summarize, I basically say I think so. And I think that arching was the clearest variable I could see here. And the Wilmot and the Plowden had respectively the highest and the lowest arching. And to me, the tonal comparison suggested that the full high arch of the Wilmot could be linked with its lowered mid-range and strong high-range output compared to the low arch of the Plowden. So secondly, can the new violins capture the characteristics of the old violins? Well, I would say yes. That's my conclusion. And I also close by saying the new instruments also have some similarities to each other, which is also what you'd expect. So I'm going to move on from this, if I can figure out how to. Okay, there's lots more stuff in Strad3D. So the question is, where have we gone from then? So I'm going to start showing some of our work here, and there's three main themes that persist from Bissinger's work. One is, where does the energy go in, and how does the energy go in, and how does it come out? And to do that in part, let's see what I have up first. Yes. All right. One question is, we know what comes out, but that's only part of the motion of the violin. It is arguable, and I think an insight that has come, sort of been emerging, is that the feel of the violin is a very different reality to the sound of the violin. The sound of the violin is what comes out of the violin and is heard in the room by the listener. The feel of the violin pretty much comes down to what the player feels under their fingers, particularly the bow. So one way to track that would be to, let's see, I'm going to just go ahead here. Yeah, I'm just going to show you my setup. Dr. Bissinger, when he came to George, I'm going to call him, as we all call him, when he came to the Oberlin Acoustics workshop for many years, and he brought his mobile rig, which was a little array of 6 microphones, and then he would take the radiation of top and then back, and at the same time he had 2 accelerometers that he would stick at the same time behind each foot, so he could capture the radiation and the mobility. And I've tried to, I guess, mimic that to the best I can in my own setup. Once again, I will just say the caveat is we do the best we can, but I'll never swear that my calibration is perfect. I tend to prefer my measurements when they're taken in very short proximity in time, so nothing can shift. So right here, this is the real Strad Titian compared to a copy I made of it. And what am I looking at here?
The real Strad is red, and then yours is black.
Okay.
This is post mobility on top. So these 2 lines are the mobility of the post,
Okay.
and then this is the radiation.
Okay.
The previous slide shows the bar mobility.
Okay. Let's go to that. All right. What we have here, I'm going to try to make it a little bigger if I can.
Don't think you can.
Okay, I can. Here, down below, is the radiation. The Strad is in black in this case, and the new violin is in, no, I'm sorry.
Strad is red.
Strad is red, Zyg is black, just like in the other images you saw. We were consistent, which was good of us. Thank you, MJ. A lot of the stuff I'm showing you now is processed by MJ Kwan, and thanks for that.
You're welcome.
The radiation for comparing the 2 fiddles is down below, and the mobility taken on the bass bar side is shown above. Now, just looking at the radiation here, this is similar to what I showed you before, and little differences. The Strad has a clearer and fuller A0, which probably makes it sound a little boomier. You win some, you lose some, basically. If you compare those 2 spectra, I'd say it would be, I would say in this particular test, my fiddle has a couple of big spikes near the projection transition hill region, so it might give it a little bit of a reedier feeling. And anyway, you win some, you lose some. But then when you go to the mobility on the bass bar side, particularly, like, let's say here at the B1 plus, well, it's arguable that they're pretty neck and neck, but it's arguable that the Strad pops up just a little bit. But on the mobility, that's how much it's moving at the bass bar. The new fiddle is moving more at the bass bar. If we just focus on the B1 plus tends to be the most problematic mode because it moves so much, and the wolf has been very discussed here, and that's where you're going to get your wolf. So in a certain point, it's nice to have a lot of radiation on there, makes your fiddle sound warm. But if you have a lot of mobility, it means that you're going to have potentially more playability issues. So, of course, when I compare a Strad to my own fiddle, my default position is I want to like the Strad more because that's what we like to do. And it's immodest to not do that. But anyway, in this case, I could say, just looking at how much more mobility there is on my fiddle here compared to the Strad, I might posit that the Strad is probably a little more rigid in some ways and is more efficient, if that's the right word, in that it moves less at the bridge for the amount of sound that's putting out. So the mobility is giving me another view of the instrument. This is on the post side. One of the things it's interesting to test the mobility separately. Oof. What just happened there?
Go back.
Thank you. On the post side and the bass bar side, there's bass bar, post. And if you just consider the, that's the mobility on the B1 plus. On the post side, it dives down like a lot. So, which is kind of what we'd expect, that because you have the post there, you're getting very little there. But sometimes you get some. What's interesting in this case is that you see other little features which I can't fully explain. I'm sure if George Stepani here, he could analyze that violin as like, what is this other mode here, which you see as a little shoulder on the radiation, but showing up in the post mobility pretty strongly, that's higher than the B1 plus. That's not a mode that we were looking for. It would be interesting to track what is that. So I'm going to move on from this. Well, there's my setup. I think I showed that to you. Backtracking a little bit, you know, to the question of can you characterize timbre based on model? And, you know, for Guarneri and Strad, frankly, it's pretty easy. But can you do it between different types of Strad models? So two Strad models I'm using these days are the Kreutzer, which is a late Strad, sort of similar to the Wilmot, full arching, tends to be graduated a bit thinner, and the Titian. So could you see differences in the between the Titian and the Wilmot, and the Kreutzer models made here by me, or would those differences just be swallowed up by other construction details, of which there are many? Tell me what I'm looking here, please.
Oh, sorry.
Oh, one's detail and one's averaged?
So yeah, so this this page is 7 different instruments. All of the blue ones are Kreutzer models and all the red ones are Titians. And then this is the blue line is the average of the Kreutzers, and the red ones are the average of the 4 Titians.
Nice.
And
Okay.
then over here there's band averages.
Cool. Okay, so we're going to look at those again, but just looking, that makes sense now. So all the reds are Titian models, all the blues are Kreutzer models. And there's certain things that pop out here at the upper end of the, you know, at this, I don't really know what the frequency here is. That's probably in the around 2000, I'm guessing.
Yeah.
So the Kreutzer models are quite strong there, and they're also pretty low here in the transition hill presence region, which all things that I would sort of expect. So you'd expect the Kreutzer models to be a little smoother because they're lower in the projection transition region. And interestingly, the Kreutzers are kind of a little bifurcated. Some of them have a second high hill that extends a little further. So, so just to summarize, and one to quibble with it, but I would say these models are breeding pretty true, you would say, if you were talking about show dogs. I mean, they do follow, you know, their anatomy. This is what we just looked at, but all the reds are averaged, all the blues are averaged. This is what I'd like to do more of. Now, skip that. I'll just at this point, I'll just say, this is a grab bag of some of the stuff that we've done after this, which I think either relates to the tracking the energy or tracking the structure. I would love to hear from anyone here who's got who's doing similar work, different work that we should know about, or good critiques of our work. That's really what I'm hoping to come out of this, and I hope there'll be some in the discussion, or contact me later. This was I often give well, you know, at the acoustics workshop, I often give a setup lecture because my experience is more about practical acoustics, if you will. And one of the things we were talking about is like a lot of lore that, as I learned it, is this: if you pull the Soundpost further out and fit it further out, you'll accentuate the bass, and by activating the bass bar is the way I thought of it. So we decided, could we test that, and would we get it? And we had the Anima Nova Soundposts, which enabled us, we calculated how much, if you move a Soundpost out 1 millimeter, but you want the same tension, relative tension on the top and back, how much shorter would it have to be as you come out? And it was pretty easy in the end. I had never thought about it, but if you just measure a Soundpost on the inside and on the outside, you have 2 numbers, and you measure, get the thickness of the Soundpost, you can calculate how rapidly it's declining or raising. So we were able to use the Animanova Soundpost, do an experiment with pretty significant motions, and try to adjust the Soundpost so it would have the same relative tension, so it would be less of a variable to just the fact that we were cranking the whole arch with the Soundpost. So that was the nature of this experiment. I was I the advisor?
You started it.
Right, but anyway, I didn't do the testing, and there were people. So let's just show some of the results. These are 3 positions. These are all the violins?
I think this is one violin.
Okay.
I don't know.
So once again, green is inside the bridge foot 5 millimeters. Purple or whatever that color is, greenish. That's black? Black is 1 millimeter inside, and red is 3 millimeters outside. What was, and this is sound radiation. So as far as radiation, pulling the Soundpost further out did give us a little bit of an edge, and also more in the transition projection region. And Bridge Hill, you win some, you lose some. In the upper Bridge Hill, it's doing well, and the lower Bridge Hill, it's hard. So they're not dramatic differences, but you can say it did follow type. Now,
individual peaks, then, like B1 minus B1 plus.
Right. Okay. Right. So where we would expect the most differences is in the signature region, because it does create more asymmetry. So there's a 0, and it's sort of like far inside, down at the bottom, a little further up, higher and red, yet higher yet as it comes out. All through here, that is, it's nice and linear, especially the B1 plus more than any, but the B1 minus, excuse me. B1 plus, some of them are less clear. This one is very clear and very satisfying. Is this just, this is a graphic that MJ came up with for, why don't you explain it?
We basically, if you take the difference between the 2 extremes, so the position way outside the bridge foot and then the position way inside, if you sort of subtract this, then you'll see the difference there. So you'll see how it moves. In general, you see with the outside position over the inside position, there's just generally a positive change. And then there's a few places where it's a negative change.
Nice. Okay, and the next, so then we decided to track radiation, mobility. There were some issues. I don't remember what the issues with the laser were, but this was a very pleasant surprise, which is, and I'm not claiming this for a general trend that will work on every violin. Is this Marcus's?
I think so.
I think this is one violin, if I'm not mistaken, but we liked it because it behaved in a way that we approved of. So while this violin gained radiation in the B1 plus, it lowered mobility at the B1 plus. That is a win-win, I believe. If I measured it, if it was measured correctly, and if I'm interpreting it correctly, it means more sound is coming out, but less wiggle waggle weird stuff is happening under the bow, and it would feel more focused and more controlled. So these little band lines seem to show that as a trend throughout the lower range and through all these ranges. Now it just happened to work out in this case, but that was really interesting that you could change the mobility. This was bar and post mobility. It was tested in only one way. This was super promising. And I think, to me, with many of these things, they really are everything's interesting, but they're really interesting when you can do something about it. You can compare before and after. because otherwise, to a violin maker, a graph is a bunch of wavy lines. But if you can do a change and you like it better and you can see the difference, and then you can fit it into a theoretical framework to boot, you're really beginning to put something together. So that was that test. I'm going to come back to this image. Hold on. Yeah, I'll come back to that in a second. So I'll show you maybe one more thing. I didn't look at my outline, so I don't know what I'm forgetting. But like many of you, I keep a spreadsheet, have for a long time, and little by little it is growing. And there's always a question of what should you include on your, I'm going to make this nice. What did I just do? Okay, I'm going to undo whatever I just did.
I don't know what you did, but oh well, let's just make it giant. If you want it.
No, I don't want giant. I don't want giant.
You want a little.
Yeah, I want a little. Right.
Okay. Too little.
Too little.
It's okay.
Okay, fine. There's all the usual stuff on there. And we're looking for patterns. Why won't this slide now? Oh, did I just?
You did. Yeah.
Okay. So just, I'm not going to discuss this in detail, but so the back, density, how much it weighed, M5, M2, top density, and how much it weighed, M5, M2, top with bar, top differential with bar. And then I started using Harris numbers, Harris number without bar. I also kludged up the Harris number by, instead of conflating, if that's the right word, mode 5 and mode 2, usually you add them together and then divide them by 2, so you have both. I did it with just mode 5 and separately just with mode 2, seeing if one of those numbers would be more significant. There's the back Harris, there's the average of the top and back Harris, wood properties, etc. Why is things being so kludgy? Okay, here we go. One of the things that, Claudia, we'd love to talk to you more about this, because one of the questions is, none of this really means much unless you can say something meaningful about, not only whether you like it or not, but whether it was good in various ways. So maybe I'll blow this up a little bit. Okay. Okay, right. So, I do keep a lot of notes. They're not always, I usually just write comments. And then I, like many violin makers, I thought, well, if I have a spreadsheet, I should think of main characters: dark, bright, edgy, powerful. I think, Claudia, one thing that you've worked with that we've tried to observe, and MJ has pointed this out a lot, is that when you set up limited categories, it sort of dictates, you respond to the categories you've set up. So as an experiment here a little bit, MJ's been doing this, but like there's my words, and then my, like, if I have any real big thoughts about it, we'll put the ranking here, and then she has categorized how often I use various words. For example, 4 is like my codes are not always consistent, but 4 stars was like I liked it a lot. More recently, a big smiley face means like everybody liked it a lot. A face with a little question mark means we're not so sure. And this is it's not an outright frown, but it's like one side is up and one side is down. And like on this fiddle, it was like a little gummy and maybe not as clear as I wanted. And then I also have regrads. So and then there's all the words that I like to use: very snappy, brilliant, open, boomy, a little edgy, focused, clear, edgy. And so there's my words, and then here they've been put in categories. Like, so how often did I say brilliant? And here it appears. And then she's having done all this, I want to go to my PowerPoint again for a second. And then I want to go to this, which is MJ, we were trying to, like, one of the things that I was trying to make my spreadsheet do for a long time, and MJ has helped accelerate, is not just capture a lot of data that we don't know what to do with, but begin to process it and to calculate it. So the Harris numbers are an attempt to process data and make sense out of them. And so MJ, why don't you describe this chart?
Yeah, so this one, you know, we have that big collection of words that we've used. And I wanted to see if they had any correlation with anything. Well, for this one, we chose to look at it versus density at the bottom here, density of the top and the speed of sound of the top. So these diagonal lines are sort of me like penciling in where the radiation ratio ends up. So basically, you know, if you have like a very low density and super fast piece of wood, then you'll have a very high radiation ratio. And so then these little markers and stuff, these other diagonal lines are what happens with the modulus of elasticity of the wood as measured when we start out. Yeah, so here's our meh face. Ones are shown as little blue dots. So these are like of the resulting instruments. The red dots, red squares are the ones that we really liked, and then the green ones we didn't, you know, have like, it wasn't extreme. And so we want to see if all of the happy face ones, you know, have any sort of correlation with the wood properties. So in general, the red ones are in fact like, you know, higher radiation ratio, and then the meth face ones, that's what we're calling it. The meth face ones are lower radiation ratio.
Sad more than that.
Yeah. The program gave me these, like, I mean, like the Excel gave me these best fit lines. So like, I don't know if you take these away, like if you would really see, like, you know, I would see separation between the red stuff and the blue stuff, but it is kind of, you know, a scattery thing. So don't, you know, take these lines with a grain of salt. But the other thing I did, and I did this manually because I don't know how to do it like in the program, is I looked at the violins that, you know, have higher speeds of sound, and then just collected the words that, oh yeah, so like in the chart you can like sort the wood properties. You can sort all of the violins by wood properties. So if you sort it from fast to slow piece of wood, then at the top you'll get these words more often: smooth, focus, bright, big, dark, clear. And then at the bottom you might get something like speed, massive. So with lower speed, then you get like massive, thick, intense. You see those words pop up more with a lower speed of sound. With a lower radiation ratio, you get words more often like focused, not open. Focused, not open, strong, smooth. And then with a higher radiation ratio, the words that would pop up more often are dark, open, big, clear, unfocused, thick, and bright. If you sort it by modulus of elasticity, then the higher modulus ones usually turn out boomy, or like the word boomy would show up more often is what I would say. And then with lower modulus of elasticity, the words that we saw more often pop up were bright, edgy, and lightweight.
Cool. Well, I was very excited by this. I mean, one thing, just for the usual caveats, is I first of all haven't entered all my instruments in here, so this is still, even in my own instruments, a limited data set. But you know, it's one of these things. It's like I would categorize this as interesting if true, and kind of the first result, if you will, not the first result, but a result from. We call the spreadsheet the magic 8 ball because we want to shake it and have an answer come out. This is the kind of answers I want. You know, we want it to be not only descriptive but predictive when you're working. So I'm going to move on from this. I'm going to show you one more thing, if I may. I'm sorry it's so much stuff. This should have been 4 talks. But one more really cool thing that we have been doing is one thing is that looking at spectra, it's sort of like band averages. You look at one spectra after another, it's a lot of wiggly lines. And how do you even remember all those? What have I done here? And how can you compare a lot of spectra without going crazy? But I don't see enough of this. Maybe we should reduce it by okay. Right. So one thing is that like there's different data sets. Like normally, like we've been putting more and more of like the stuff I normally would just keep on a piece of paper about my violins has been working its way into the spreadsheet, which is nice to compare fiddles. The one thing that has been very hard to incorporate is spectra. And I find spectra are like whatever I'm trying to think of now that I can't remember. Because because once you look at a bunch of them and afterwards you have a vague impression of what you thought you saw, but you can't really remember them accurately enough. So how could you import spectra into your spreadsheet? A, without crashing your spreadsheet instantly, and B, in a way that without so much detail that, that you couldn't assimilate it, and in a way that you could look at a lot of it at the same time. I will actually enlarge this for 1 second. Was it 200 before? There we go. What we have here is each of these lines is one violin. We have smoothed it in half semitone chunks and then imported that data into Excel and then somehow made it show up in a color band scheme where blue is the least amplitude and red is the most amplitude. And then this is basically, we'll just take that one line, is a spectra. We've put in these little things for reference. There's A0 is like around here. That's like it's actually, yeah, 270 here. And then there's usually a little dip in here. I don't know what you call this thing. And then B1, that's CBR would be around here probably, 375. And then B1 minus would be in here. And then B1 plus is in here. So what I've tried to do is I've tried to just create little bands just to look at them. And this is like usually a little hole. This I've just named these according to what I think I often see. There's what I call transition hill low from like 795 to 900 basically, and transition hill high from 920 to 1130 or something. And then there's the low ditch and the high ditch. And then there is, I haven't given this thing a name yet, maybe someone else already has, 18 to 23. It's a very persistent feature that you see in most fiddles. It's really like maybe the most powerful part of the bridge hill very often. So far we haven't given it a name. I'm calling it 18 to 23 now. We could call it the underhill, whatever. Then there's the lower hill, which goes from around 23 to 28, upper bridge hill and treble slope, and then who knows what. So that's just our names for it. Doesn't mean anything. What we see here is just pure data. And these are all different fiddles. And it's like, so interestingly, we were talking about Titians versus Kreutzers. So these are all Titians up at the top. These are all Kreutzers. And these are all Del Jesus. Now it's just a few that we've managed to enter so far. But if you just, well, what do they call it? There's a word for when you see when you see things that aren't really there because you have your pattern forming brain. Anyway, there's a word for it. No.
Yeah.
Anyway, it's like why we see like a stop sign looks like a smiley face to us or an angry face. Or anyway, well, okay. So down here on the A0s, which you don't, they're not the strongest ones, but they're there. Okay, well, just for example, the Kreutzers over here, I would say this little band here, which is pretty much my 18 to 23 band, is the strongest on the Kreutzers, whereas these ones, it's a little more diffuse, maybe. On the Deljasus, I would also say it's a little more diffuse, whereas these ones, that's a pretty consistent looking feature of that model. I think I see here in the low ditch, this might be pushing it statistically, but I think I see more blue and green, like a little more of a dip through there. At the transition hill, I don't know, it's kind of arguable. The Titians maybe have a little bit of a stronger band right here. The Plowdens, not the Plowdens, the Guarneris, I would say, do have a little more of a transition here. One thing I like to look for, there often is on fiddles, a low spot somewhere in the ditch. But it can vary. And I think on a lot of, so on the Strad, I think like this blue area here lies, these are the Kreutzers, pretty firmly in the low ditch. And on the Guarneris, I would like to say it falls more maybe in the high ditch. And then you can compare individual fiddles, etc. I think this might be where I stop talking and let someone else talk. And I invite anyone who is working on any of these things or has comments about them, if we run out of time, contact me as well. But let's open up the floor, and I'm going to close my screen now.
All right. First, let's give Sam a big round of applause. Thank you so much. Wow. So just a reminder, if you have questions, please use the raise hand function, which on my app, where's my raise hand, is in the reactions icon on the bottom. It may not be there in your app. So first question is from Joseph.
Can you hear me okay?
Yes.
Oh, yeah. Thanks, Sam. Super interesting. When you were looking at that sort of handmade spreadsheet that MJ made relating radiation ratio to your adjectives, I was surprised. Maybe I got this wrong, but it looked like that low radiation correlated with focus and things like that, and high radiation ratio with boomy and unfocused. I would have thought the opposite is true.
Well, not necessarily, actually. I mean, okay, in all interpretation, all with a grain of salt. But high radiation ratio probably means low weight, low density, right? And low density will pretty reliably have big low modes and be very full sounding. And I have often struggled with light tops being wolfy and unfocused. So in a way, fullness is often correlated with a lot of motion and unfocusedness. And some fiddles that are the easiest to handle are I think, often have denser wood or heavier plates than I would have thought, because they handle really well. Is Nathan on a line by any chance?
No.
But Nathan had a Guarneri model of mine, which I thought was a good sounding fiddle, and he traded it in for an old Strad model of mine, which had some of the heaviest plates I've made. And he feels super comfortable with it because it's super well behaved. And so I think I think that is actually consistent, that high radiation ratio would be boomy and unfocused.
Okay, and the range you were using, I think, went from 14 to 17. Is that about right?
Yeah, I'd say so. 17 is pretty rare, below 14. I have to say, I mean, I was actually surprised that it actually showed up as in the results as well, because I've been discounting radiation ratio as much of a factor, because it was picking wood by radiation ratio was just making me pick low density wood, which was not giving me the focus that I wanted. So as a single criteria, I found it was, I was being led by the criteria and not getting the results I wanted. I think other makers had that experience as well. When we found out about radiation ratio, a lot of people picked super light wood and then found some issues with it.
Okay, and just one other comment with the Spectra you're doing, comparing the violins,
right,
and what you called the lower bridge hill.
Yes.
In my experience, that is where the bridge hill radiates most strongly by far across a wide range of violins.
Is that the 18 to 23 with the one?
Yes, and then the admittance bridge hill is higher. It tends to be around 2.5. So the efficiency is such that it radiates at the lower edge of the bridge hill. So I was glad to see yours confirms what I've seen.
Yeah, absolutely. Should I pick, or Fan, are you going to pick?
Yeah. We have a queue. Joseph, are you done?
Yeah.
Sure. Yeah.
Thank you. Next is Doug Martin.
Doug.
Yeah, thank you, Sam. A great gift. I've been calling around 1800 the Orbison.
I like it.
What's that?
And I found, because I identify that as prominent in his voice.
Roy Orbison.
Oh, okay.
And I find, what I have available, I found Francis Scott is the only of the great masters I heard in personally, and now I think it's the Hart Strad he played a lot, and Augustin Dumay has that now, but that has a strong peak around 1800 also.
Well, the only problem, this happens to me all the time, I'll say, oh, that's something, like you just said, Roy Orbison, and MJ said, who?
But no. Okay, I didn't catch that.
Okay.
Good, I'm over.
And
All right.
I just want to mention that Gluey was largely, it's not a direct takeoff, but was really inspired by Doug Martin's work. I mean, that was, Doug, when you started bringing your fiddles and just like, adding pieces onto them, sawing them off, and just to see how with the freedom with which you worked, I found that almost heartbreakingly moving. So thank you.
Well, I'm gratified. Thank you.
So Sam, since you mentioned Gluey, Jeffrey Solo in the chat said, early on in your talk, when you showed applying reinforcements to change/improve the sound, what
Right.
sort of changes did you get with reinforcements?
Well, it's in this particular case, first of all, the reinforcements are very small and very thin. They were like basically not thicker than a repair stud, and anywhere from a few millimeters to centimeter long, basically, or usually. The biggest, I was just looking at it again now, I saw that the amplitudes of a lot of modes changed, but the frequency of the low modes didn't change all that much because I don't think they're big enough or stiff enough to really move the frequency of the low modes. But the amplitude of the high modes changed quite a lot in this particular example because I think you're creating a lot of little microclimates of stiffness. Like anytime you have a little stiff area right next to it, it's like it's creating all these little pockets of stiffness and surrounded by what was flexible. So just specifically, it mostly was in high frequency stuff. In this particular case. And one thing just to say about Gluey is on purpose, it was a very thin fiddle so that the changes would make a difference.
All right. Thank you. Claudia?
Yeah, thanks for the nice talk. Particularly liked the end with what you've done with MJ about trying to put all your violins on the same chart. Because I think the value of it is that it's all your violins and it's all you making the comments. So probably over the years, you may actually change as well your way of describing things. And so maybe there can be some shift. But when I did the listening test on the violas, I tried to do some similar charts, and basically it was all over the place. So I was not surprised to see your red and dots and blue and green kind of all over the place. It seems still that you, with some of the vocabulary, you are able to put them in the corners. So maybe it would be interesting to look a bit further into this. And I have a question about this because you said the radiation, you said the Young modulus. Was it like an average Young modulus of the top and the back, or was it?
Well, that's a good question. I don't even know.
No, it's only the top, and
It's only the top.
Yeah.
Okay.
I mean, one thing I have to say that is the dark secret of all acoustics work is that you do all this work and then it's like, I remember the OB Alto project and your presentation on it. Well, we carefully tabulated this, but no, we didn't find anything. And right. So it's like plowing a field and planting crops, and like, one little weed comes up, and for a long time. And you have to have faith somehow. But I mean, I still feel like, and I don't know what it is, but some very key variables are still escaping me construction-wise. It's partly, though, I think that the putting the spectra on a spreadsheet is potentially a big improvement, because it is, instead of focusing just on the subjective, it is like, you can have a good fiddle that has a specific characteristic, and you could have a bad fiddle that also has that characteristic, but maybe it lacks something else. So I in the longer run, I want to be able to say, you do this, you get a little more in this specific frequency region, even if I didn't like it. That's why with that article that I wrote recently, I tried to correlate with very specific regions, and I also chose my regions, my bands, not from psychoacoustic reasons, but just from like just where I see hills on a spectra, just purely taking the physical, what I see, like there's something here and there's a dip here, and yeah, it is slow going. I mean,
but I mean, yeah. So in terms of vocabulary, if I may, just
yes, please.
One of the last experiments we've done in a workshop 2 weeks ago, and I was hoping we could redo some at Oberlin this year, but it's not going to happen. So I don't know when, but but so because we were like puzzled by the fact that yes, we hear clear differences, but then when you want to test them in a robust way, and you try to do it a few times to make sure that you really do hear them, we can never do it. Okay, like if we do it 8 times, you cannot make more than one mistake. Otherwise, that you can't show that it's statistically significant. And so to do it 8 times and only one mistake, it's very tough. And we always make more mistakes, meaning that we can't even separate 2 different violins.
Do you mean that one player retesting again?
One player testing 2 violins, and you have to say if it's violin A or violin B, we can't do it. Even when we took like very, very obvious violin, we thought, okay, we take this one because it's dark, we take this one because it's bright. And by the 8th time, everybody was, or almost everybody was confused. And so this week, we thought, 2 weeks ago, we thought, okay, let's maybe do some in another way. So this time we actually ask people, or like, for example, a violin maker or a player, to describe 2 violins. And then we heard these 2 violins played, and we had to tell which one was which. So we got a description of, okay, this violin has a bright end and doing this and that, and this other violin sounds more like a trumpet, or our player actually uses. And that was really funny, because when we actually did it, everybody got it right. So we had a verbal description of 2 violins. We heard the 2 violins, and we had to associate a verbal description, which violin corresponded to which verbal description. And then we were able to do it. And so we thought, okay, so we do hear something which makes sense, and we are able to describe it. And then we said, okay, let's put a 3rd violin. And then we were lost. So we actually played 3 violins, and we had to say, okay, which of the 2 were originally played? Okay, so for example, the trumpet violin was B and the other violin was A. And then we put a violin C, and then we had to say, okay, which was A and which was B, and then we got completely confused. So when you narrow down to 2 violins and you describe it, and people really can associate a verbal description to, and especially if the 2 violins are a bit different in terms of character. But as soon as you introduce more complexity and you add another violin, it's just like a total mess.
But I mean, there's a conclusion from that, which is to keep the tests really simple, that people are pretty good, like A, B, A, B. And I think it may have been one of your colleagues who wrote an article, a paper about specifying, like when musicians play something, telling them what they had to play to more efficiently judge sound, not letting them free play excerpts, but play specific notes.
Yeah.
And that improved their accuracy quite a bit. And it is one thing which I'm curious about, for myself, even with the Alto project, I played all those violas, and based on just my impression of them, I don't actually know, but I felt that if I had to categorize them, I could have done it because it was only my own taste. I didn't have to average in anything, and it was basically my own playing, which I have to say personally, maybe my ears aren't that great. I don't know. I can tell far more reliably just playing something than I can listening to it.
Yes.
The playing.
I'm sure that's one of the problems of playing.
Right. So it's
of listening. So, yeah. When you listen, you don't, because by playing, you know as well what you're expecting for. When you feel, when you start bowing on it, you expect for something, and then if it does correspond to your expectation or not, you can get some judgment, which is probably easier to correlate with some of your own feelings and expectations than when you're just listening, because you have only half of the feedback to some extent.
Right. So it's, one of the issues with all this work, and I am curious to hear more from you about, like, we know how to make these tests harder and more unreliable, but how do we make them, like, I'll just describe it. Like, one year in Oberlin, Da Hong Situ was visiting, and there was, I don't know if you were there, if it was Joseph, but we did some of the first line tests. And most people, I think George Yu with the exception, people couldn't tell what violin was what in blind tests. And everyone was disappointed with themselves. But then we went to Baldwin in the living room there with Da Hong, and we just handed the violins around, and he played them, and we talked about it. And we felt like we could reach consensus on what we thought about them. So it either was group hypnosis, or we were able to extract by consensus a feeling about these violins. So that's a question. If it's not, like I said, it's like we know how to make the test hard, but how can we make them, like, really revealing?
I know, and that's why we were trying to make it as easy as possible so we could all get 8 correct answers, But we haven't been able to find a way. Well,
maybe one of the answers,
we did by comparing a viola and a violin.
Right. But once in a while, for some reason, like, a lot of violins will be here for the same time, and we'll, like, put them all out on the piano and play a bunch of violins. And I have to say, it isn't all that fruitful. It's much better just to have 1 or 2 violins, as you say. So maybe the answer is, like, just 1 and 1, and just comparisons, like, tennis matches, and see who comes out of the multiple things. And
but at the same time, then it's very hard to know what is due to what, because between the 2 violins, almost everything has changed. So how do you know that the difference in character is because of this or because of that?
Yeah.
So anyway, there are other people waiting for.
Yeah.
All right.
Thank you.
Thanks. We can talk about it again later.
Yes, please.
Thank you, Claudia. Next is Colin.
Colin.
Thanks very much, Sam. It's a fantastic talk. There's so much in it that I'd love to talk to you about. But one simple question that I'd like to ask is to when you're copying your particular instruments and getting amazingly consistent results between the original instrument and the copy, what are you actually doing to do that? Are you taking the original plate tunings that from the original instrument and copying those? You've already said you're using the same arching, which I'm sure is important. Or to what extent do you actually have to fiddle around afterwards in the setup to get that?
Thank you for the question. For the most part, I don't know what the plate tunings are, and I haven't disassembled the instrument. Right. As far as the arching, I do try to come quite close, but I will say that there's a lot of distortion that I won't copy completely because it's a moving target. The instruments continue to distort, so I can't copy it completely. So even that varies a little bit. Because of CT scans in these cases, I know something about the density of the wood at least. So I can try to match the density. I can try, if I have what I feel is similar density, I can try to match thicknesses, which I've measured with a Hacklinger usually. I will confess when it comes time to graduate and things, like I'll follow patterns, but I think I'm constitutionally unable to really follow the numbers completely because yeah. But that being said, like on the Titian, based on like I showed, I think that based on the fact that the copy maybe was more, had more mobility in some regions and also more of a dip in the mid-range, that I may have been a little more flexible than the original. And probably I didn't make a huge, massive bass bar in the new one like the original did. Mm-hmm. So, I mean, differences do creep in. So what I think my point in that was not to say I'm going to reproduce this violin 100%. It was like, will the three copies made along the same lines have similar relationships to each other as the three old violins? Which I think you could fairly say that they had similar relationships without being identical to the original.
Thank you. Other people want to come in.
All right, thank you, Colin. Jesus.
Thank you, Fan. Thank you, Sam, for the talk. I have a request more
yes.
than a question. In the scans available in the project, we have only some words about the exact position of the CT scans. We have only words like widest upper bout Plauen, and then we have the slice to see the arching profile, but we don't know exactly where the slide
right
was taken. So can we obtain this information in this point of the project?
Well, one place you could look is on the project. There's also axial videos of the violins, and if you went through the videos, you could locate the slice number, and you could make your own cross sections. Because you know what I mean. If you started the violin and just like when I took them in the first place, I think actually Steve Sir may have processed some of the ones there. When I talked about widest, I just came up until like that's the widest point. It wasn't strictly measured. But because you have the videos there, you know, on the video, there's, I think, I have to look, but I think there's a slice number, and you could just choose your position pretty easily.
Okay. Well,
or contact me, and I'll try to get the information for you.
Okay, thank you. In fact, I think that more people could be interested with this information. Because in fact, last year, Sebastian Gonzalez, I can see here in this talk, we were trying to copy the arching profile of the Plauen, and we have this problem that we don't know where is exactly the slices which is currently available in files, in 6 or 7 files. So maybe the exact position with a reference to the bridge, maybe, or something like that.
Right. I honestly don't remember what's on the posters. Do you have the posters?
The files, in fact. I don't know if you can see my screen.
Great, but I mean, what I was saying is that I also put this information on Strad magazine posters. And I may have, I honestly don't remember, but it may indicate on the outline where the position is. I don't recall.
Okay, let me see in the posters.
Yeah, take a look, but feel free to contact me and I can try to help you locate them.
Okay, thank you.
My pleasure.
All right. David? You're muted, David.
Meeting.
Okay, we can hear you now.
Okay, thanks. Hi, Sam. I have heard or read claims that on fruit plate, on some of the really nice Strads and Warneries, you don't get a real clear cap tone, say for modes 2 and 5. Instead of it's more of a thump. Do you have any thoughts on that or comments on your observations?
I'll comment, but to be honest, I haven't been thumping old plates for the last years very much. I think it is more true, and occasionally I'll have a plate that is a little more like that. for reasons I don't know. One thing that I think is different is that most old violins are covered with all kinds of repairs and patches and studs and all kinds of things that could break up a nice even ring. So I would speculate that that might be part of the reason. Yeah, and that makes sense to me. I think actually having the really strong modes somewhat broken up a little bit so that might be beneficial, and having super clear, super ringy, sharp peaks.
Okay, thanks.
Thank you, David. Dimitri.
Yes, thank you very much, Sam, for your brilliant talk. A lot of information, very interesting. I guess I have a couple of questions. The first one being about the Soundpost position 3 millimeters out of the bridge foot, and it was really interesting to hear in your previous talk about the violin setup when you said that you usually put your Soundpost around 1 millimeter inside the bridge foot versus regular like 2.5, I would say, which is we can see more often, I guess. And at this point, I thought, well, it makes sense if it's a bass bar like 1 millimeter inside the bridge foot and Soundpost around 1 millimeter bridge foot. I don't know why I see that. Why I want to see the pattern here, because obviously the Soundpost is behind bridge foot and bass bar is under the bridge foot. But I guess less symmetry is better. So in this case, it really makes sense that like 3 millimeters outside the bridge foot will be good, and your data shows that. So what can we make out of this? Is it structurally acceptable to put Soundpost so far away, and should we look at this variant at all? What do you think?
Yeah, thank you for the question. First of all, to clarify, that was part of a test, and we did not leave the violin like that permanently. We made really big changes just so we could see the differences. That being said, I know that there's many makers who have a kind of a rule that the Soundpost should be the same as the bass bar in or another fixed number. And my teacher, Rene Morel, was very, one of his big teachings is that you can't follow rules with sound. You follow, well, there's limits. Like, I think structurally having the Soundpost 3 millimeters outside could be a problem just because the bridge is not supporting it on the outside. And, I think could be structural issues. So there's some realistic limits. However, if you listen to the musician and you try different things, you get an answer. And I think the position of the Soundpost doesn't know how far in the bass bar is. The saying it's the same position, it's like, it's what we call a rule of thumb. It's not a bad starting point in the absence of more information. So, and you could say the position of the bass bar is a little bit of a proxy for how stiff the bass bar is. Because if the bass bar is further out from the center, it is likely to be a little stiffer in that position. Therefore, maybe it would make sense to have a Soundpost further out. However, I just think it isn't about where the bass bar is. It's about how the Soundpost feels the stiffness and the island on that side.
But yeah, I guess that makes sense.
Yeah, but I mean, so anyway, to say 1 mil, to make the post even with the edge of the bridge foot is no problem. But it's not every violin that needs to have that.
Yeah, that's interesting. And my second question was about this CBR. How do you think which characteristics of the instrument make the CBR mode show up on the sound radiation spectrum? Because usually we don't see it at all, but sometimes it's really a pronounced peak.
Yeah, well, George Stepani could probably speak to that better, but one of the things is that since it's a very symmetrical mode, anything that makes the instrument more unsymmetrical will, so it's normally just going like that. But if you move it so it's a little more like that, even if it's still rocking, then it will, if one side is moving more than the other, it will start to radiate. Most violins don't radiate very well there. Some do.
Yeah, great. Thank you very much.
You're very welcome.
All right, thanks, Dimitri. John?
Yes.
Hi, Sam. You talked a lot about arching and how that works. And then you said on some of your copies, you tried to copy the graduation. You know, and the question is whether a constant graduation has ever been compared with the graduations that turn up on, you know, all the Hellinger or whatever it is, contraptions that measure thickness. So is it, does it affect it to follow those precisely, or so, say, pick 2.5, 2.7, 2.9, 3.0, and just do that everywhere?
Okay, there is one thing about precedent on old instruments, is we don't always know what's important and what's not important. However, it is an assumption that I work with, is if you see something a lot on things that you like pretty well, don't disregard it out of hand. So that's the nature of precedent. Now, I don't know if you have the Jeffrey Loan book of violin graduations.
I do, actually, yeah.
If you look at the old violins, they're very, very variable. And then there's a section on modern violins, and they're like, they're all, and I keep trying to convince myself to work less evenly, because I think that, you know, the violin looks very consistent and very symmetrical to our eye, but the way it works is anything but symmetrical. So
yeah, I asked Dan Draley about that many years ago, and I said, could you give me a graduation thing? It was completely asymmetrical. It was like 2.2 on one side and 2.5 on the other, and varied front and back plates.
Well, I mean, I think, you know, it's hard for me to say that any specific pattern is important, but I think you could probably like take a handful of beams and throw it on a surface and say wherever a beam lands, you leave a thick spot, and you would be better off in making it even. I'm not joking, you know. Right.
Thank you.
You're welcome.
Colin?
Can I come back to Dimitri and the situation of the bass bar and the soundpost? They act in rather different ways, because the soundpost acts particularly at high frequencies just in the region close to the soundpost, whereas the bass bar has a large effect on all the vibrations along its length. And from my work on the finite element, looking at what actually happens when you vary the bass bar and soundpost, one finds that you need a matching, an acoustic matching of the bass bar and the soundpost to give you a good sort of bridge hill with a pronounced peak in that sort of region. Whereas if you've got only one or the other, you get pronounced peaks in completely different places for a too strong bass bar or a too strong soundpost. And it will, from the finite element computations, it would suggest you need a balance between the two. So where the balance of where you're going to put the soundpost towards the bass bar, and similarly, and the strength of the bass bar and the length of the bass bar, all these things I believe is very important in the range of frequencies from about 2 kilohertz to about 4 kilohertz. And you can see on computations very big changes, in fact, as you change the relative strengths and positions. That's just a comment.
Yes, that's very interesting. Thank you. And Sam said that the Soundpost doesn't know where the bass bar is, and I wanted to probably to write him an email with a better formulation of this question, because in some sense, I guess, just what you Colin are saying, that the Soundpost might have an idea where the bass bar is. And I remember somebody was talking about the practice giving a massage to the violin when you just when you push on the treble and bass side of the bridge.
Yeah,
it was Sam probably. Yeah. And I was thinking that maybe we should try to make the feel even, that when we're pushing one side and another, But yeah, I guess if we are not looking for the symmetrical vibrations, probably it doesn't make any sense. Probably the opposite will be better.
Well, I would comment, for example, just on that, that Becker, when he was finishing his bass bars, Carl Becker was another teacher of mine, he would clamp his top onto his back and with ribs, and without the Soundpost in, because it was just a temporary clamping, and he would push down on the bass bar, and he was just feeling, how does the bass bar feel in total clamped on the ribs? And, it should, and there's no, it's not the answer is not too stiff and not too soft. But it does mean that you could tell actually by pushing on your instrument, is it very floppy? Like sometimes you should do it gently, but you feel, oh, this is moving a lot, or it's not moving very much.
Sam, I think it's particularly the effect of the Soundpost and the bass bar on the island area, because that's the thing that's actually transmitting the energy from the strings to the instrument, and that acts as a filter, as we all know, not simply the bridge, but the bridge plus the island area, and the bass bar and the Soundpost have sort of opposite effects in rigidity on one side, and the other side, the bass bar, as it were.
Yes, well, I mean, the question is, I agree with you. The question is, how do we know what that relationship is? And so from my end, it's more like you are creating their models. I have the reality, and then I fit posts in different positions until I see what works. And that is something I used to talk about is what I call diagnostic adjustment, which is the adjustment is not only fixing the problem, but telling you about the nature of the instrument at the same time. That if you have a post that likes to be further out, it's probably telling you your bass bar is more stiff. If it doesn't like it, it's telling you your bass bar might be more flexible.
But doing the pressing, as Dimitri was saying, I think it was Dimitri, on massaging it on the island area itself is probably something that is another useful test in assessing an instrument in its early stages.
I mean, I haven't tried it, but it's entirely possible that you could have something with, a gadget with a weight, and that you could see how much it flex, and it could give you a hint.
But you could do it with your fingers to get a sense of it, and Stradivari or someone, if they wanted to,
sure,
could have done it. And I mean, it's just amazing what information you can get, of course, from just pressing down on something, twisting something. You're not getting that. You're getting the same sort of information that you get from plate tuning and things like that in a rather simple, instinctive way, which for a maker is, I assume, one of the things that allows them to make great instruments.
Yes, it's funny, things like that, like flexing is a very, if you do it a lot, and then you keep the feeling good. But like if I'm graduating a top, for example, and I start graduating backs, all of a sudden the back feels rather stiff to me. If I go back to the top, I thought it was firm, and I go back, it's just so flexible, because it's all relative,
I'm particularly interested in fact, the island area, because it's the island area and at high frequencies, in particular, that is very important in determining the high frequency performance.
Yes, quite.
So this sort of twisting, flexing, I think is of secondary importance.
Agreed.
All right, let's go to George.
I was just wanting to build a little bit out on what Colin was talking about. So as we all know, if you look around different models, even among Strad models, you can find ones where the F-hole upper eyes are only like 38 millimeters apart, up to say 44 millimeters on the Kreutzer. So you've got quite a lot of choice about exactly where you put the bass bar. So I would say that it is quite a simple relationship in that if you put it further away from the center line, it can actually be less stiff. And the less stiff, there are different ways of making it less stiff. One is the the overall height, but also its cross-section. It can be more rectangular, it can be more triangular, and you can take more scoop out from the highest point to the end. In the upper bout, you can retain a longer bit of the main height and then drop off sharply. And then some people say that if you make the ends too low, you lose some of the kind of high frequency response. So there are many details to the bass bar, but I would think its overall dimensions and position away from the center line is important. But then when we come to look at the Soundpost, the thing that's affecting that, like say a rotational stiffness at the position of the bridge feet, which is a measurement we can make, not very easy, but we can make it. The stiffness of the post is affected partly by its distance away from the center line and its relationship to the bridge foot, but it also depends on what it's sitting on the back. So, I mean, the back could have a massive, great sort of 5 millimeter area in the middle, or it could be could only be about 3.8. There's big variations. So you may find that in that case, when you've got a very thin back, you also need to pull the post out more, or maybe even pull the bottom out more than the top.
Yeah, Renee used to use that adjustment of pulling the bottom out to focus the sound quite a lot.
So Switzerland seemed to think that was actually often a better move than pulling the top out.
Well, do you have a feeling, like other things being equal, whether moving the bass bar in and out does actually make it stiffer or less stiff?
I think so. I mean, violins are pretty standardized, although we have there's quite a big range. If you start looking at basses, you can have basses that have got massively wide F-holes, and you really wouldn't want to make the bridge that had feet the same width as those F-hole-Is. I mean, so then when you look at examples of it, sometimes previous makers have put the bass bar right out to the F-hole, which creates you quite a big problem in the setup. Or they might have placed it to suit a more normal bridge, which is what I would do, because I would say, well, when I set this bass up, I want it to be possible to do it in a more reasonably normal way. I don't want to have to resort to extremes.
But just a second, I need to excuse myself for a minute. I'm happy to answer more questions. MJ, ask MJ questions for a minute.
Anyway, I just wanted to make those few comments that we're not looking at a single factor here. We're looking at a number of factors which will affect the behavior in the island. And yet another one is the actual stiffness of the island itself. I mean, when you're graduating a plate, you can grab the island, the wings of the F-hole and flex the stiffness of the island as opposed to the transverse stiffness in the bouts. And there again, perhaps the way the bottom part of the bridge is cut will affect that transverse stiffness a little bit. Anyway, I've said enough.
All right. Thanks, George. Jeffrey?
Just to piggyback on what George just said, Renee Morel said to me once that in cellos, the thing that differentiates the sound between a Montagnana model and a Strad model is the island area and the distance between the F-holes, it has nothing really to do with the overall shape of the body. It's just the distance between the F-holes. But my previous question, which I had posted in the chat, was as we're moving the Soundpost out, you're of course making it tighter, and moving the bottom of the Soundpost would do that too. Have people done experiments kind of equating, okay, and now that I've moved the Soundpost out, can I get the same effect by moving it in and making a longer and hence tighter Soundpost? I mean, there are so many variables in all this, it just boggles the mind to me.
What I miss?
Okay, so yeah, so Jeffrey's question was of course about the effects of the tightness of the Soundpost and that variable. So I don't know if you want to
versus position
that or.
Well, it's I don't feel as confident in my views as I used to. The carbon fiber adjustable soundposts were very interesting because leaving aside the material, the fact that they were adjustable in length, and people who have them seem to be sensitive to very small increments of length. And the guy who developed them was not in favor of moving them very much. So, people latch onto different variables that they like to work with. But I think there were some experiments at Oberlin that Claudia participated in, so I don't know what the results of that were. But so for sure, the tightness is important, and you can see that with a post that you can just tighten. Jeffrey in particular, it's interesting that, a lot of my cellists, aren't that many anyway, but like David Finkel, Chris Finkel, they have the carbon fiber post that they like a lot. And I find that when they also got the tools, which wasn't recommended necessarily, and left to their own devices, they made their posts much looser than they would have asked me to make them, I believe, which was very interesting to me to see how people just left to tinker worked. So the answer is it's important. I'm not going to say how it should be. I would say that ironically, instruments that are floppier probably would benefit acoustically from a tighter post, because it's not about even though they don't tolerate it as well. It's not about I don't think the instrument cares about how tight the sound post is squeezing exactly, but it's like there is you want a certain firmness in the mobility at the bridge foot. And you want to move your post until you get the firmness you need. And you might do that with position. Some instruments might already be pretty firm. Like some of my instruments, I find if I over tighten them, they lose a little bit of bloom, and then I loosen them a little bit and they seem much fuller.
Thanks. Of course, the thing that no one's discussed yet today is, aside from moving the sound post east and west, there's north and south.
Right. I have to say I don't do as much of that. Just like I say, everyone latches onto the variables they like, and they tend to stick to their variables. I do find a little bit that going further away from the bridge does help with wolves a little bit when it's further away. I don't know who described it, maybe Colin, are saying that when you move the post further away from the bridge, you're constricting the area that can move. And I think that makes sense.
It's important for the low frequency modes, certainly.
Yeah.
For the signature mode region, certainly moving the sound post north-south along the length of the instrument has a very small effect compared to transversely moving away from the F-hold edges. Much less effect.
Yeah. And also, just coming back to you for a minute, Jeffrey, with a wooden post in particular, when you move a wooden post, I don't think anyone can actually adequately describe what you are actually doing, because if you move it, it's not fit in exactly the place where it was fitted, and unless you're extremely careful, it's not going to fit the same way. So you're effectively maybe moving it much more than you think, and you're changing the amount of surface contact to the back. Like George Stepani was saying, that there's, I forget what he called it, rotational stiffness. If you just have a corner touching, then you're not getting any rotational stiffness out of the back. But if it fits very well, you're getting quite a lot. So, with the wooden post, there's little things that you do that don't seem to make any sense, like one last little tap,
Yeah.
And that make a big difference. There's no good explanation for it, but I think you're micro adjusting the fit.
Thank you.
All right. Thanks. Andrew. Andrew?
Hi there. Hi there.
Go ahead.
I just want to make a comment about Sam's comment about uneven graduations. So I would think that if you have uneven graduations, you're more likely to have a random modal, what's the word? The modes are more likely to be randomly dispersed, the upper modes, which seems advantageous to me. The more accurate the more uniform your graduations are, the more likely the modes are to follow some sort of regularity. Does that make sense?
Yeah. Well, yes. Yeah. I also used to, when, usually when I'm graduating, like here, you're like, oh, too thick, plain, too thick, plain, too thick. Oops. And that's when I know when I'm there. And we call those, the spots that you don't really want to write down on your sheet, we call them Pickering spots. And I think they help, that actually it's like a little pool of extra tweeterness in some little spot,
Yeah. So Andrew, how do you work when you graduate?
Not particularly carefully. I'm not like dialing into the 1/10 of a millimeter. I sort of say, oh, it has to be roughly this thick, and then I do it and scrape it. It's a little thick, a little thin here. That doesn't bother me because both for if you're thinking about the low modes, they don't really care if there's a little thin spot or thick spot. They just behave according to the behavior of the whole plate. And if you're talking about the higher modes, then it doesn't really matter because you can't predict those anyways. So you may as well have some randomness, which seems a good thing to me. I mean, I don't know whether that makes scientific sense, but that's my picture of it, that I can't predict the upper one, so I don't even worry about it as far as like thinking, oh, I can move the 10th mode, 5 hertz. What do I care? That's not important that it be placed exactly in a particular spot. So that would be my take.
Okay, thank you.
And the thing about the bass bar, yeah, I agree with Sam completely that the Soundpost doesn't know where the bass bar is, and this whole idea of symmetry, like it's just there is no symmetry there. Like just to start with symmetry is just like a convenient place to start, but after that it's just you just make it work. So thinking about symmetry as far as the post and the bass bar around the center line or a center point is just you're just fooling yourself.
Okay. Yeah, let's have one last formal question. So, Sam needs to go. He can go. John, I'll give you, we'll go John and then Joseph, and then we're going to go into our informal section.
John? Just to follow up on the bass bar and the O mode, or, M5. And usually when you hold M5 in the wrong place, it sort of kills it. And the bass bar, if you use a 270 millimeter bass bar, you're crossing the O-ring. Is there any advantage to shortening the bass bar so it ends where the node is?
I would like to hear other people's opinion of it. I think that the ends of the bar are very important. I have not personally varied. That's not a variable that I mess with very much. Sometimes if I have a plate that seems really stubborn and stiff and I just can't get anything to ring, I'll shorten the bar a little bit just because. I do kind of visualize like the strong ends of the bar landing not at the ends, so that they're sort of like muscling around that region of the violin. I think there's a lot more activity near the ends of the bar in the high frequencies than we're aware of. This is, I've talked about this before somewhere, but there's like, it's easy to see like in the modal animations that at low frequencies, the bar is moving like this while the sound post is staying like that. And then high frequencies, then it goes in the middle and then the post is moving like this. But what hasn't been discussed much or explored much is the fact that when the bass bar is being like, shocked like this, and it's transmitting, I believe, high frequency out to the ends of the instrument, that's not well understood.
It seemed counterintuitive. It seemed counterintuitive to me to have the bass bar cross the O-ring.
Well, have you tried shortening it, or do you have an experience with that?
I tried one on a viola, but I used that strange viola or a bass bar where you trim the bottom out in a couple of places. So I wasn't sure which one was affecting it, but it sounded good to me.
Well, that's a question for everyone here. Does anyone have experience with varying the length of the gap from the end of the bass bar?
When I'm tuning whatever it is, my bass bar, I like to check if my mode 5 goes through the bass bar, and when it does, I think it's done and it's fine. So in this case, I guess you don't have to make it short, you just have to make sure that your mode 5 nodal line goes through it, and that's okay for me.
Anybody else?
I think Baroque violins have short bass bars, and it really doesn't, I think this is leading us to nowhere really, because the effect of the bass bar on the symmetry of the free plate and with the pinned edges is much less than you'd think. It's a much smaller effect than adding the Soundpost, and the apart from its general overall sort of stiffness in the low frequency region, I think the other details of the bass bar are going to affect the performance in the high frequency more than in the low, because the bending wavelengths are very large compared to these local features, and changing a small local feature has practically zero effect on low frequencies.
To do with the ends of the bass bar, 2 comments. One reflects your findings with the Gluey sound, which is for no particular reason. Things are really sensitive at the ends of the bass bar, so I would think it makes a difference, but I wouldn't know how to generalize that difference. But the thing I've been thinking about a lot lately is creep and deformation, and I think having a Baroque style bass bar, you're probably going to get more neck sinking and things like that. So I think there's some structural reasons for wanting some stiffness towards the end.
Yeah, the other variable about that, of course, is your graduations at the end of the bar. And I was taught not to go too drastically in from the ends very gradually, so they're sort of thick. So you could, with my own instruments, probably pretty often you have a thick graduation rising or descending from the blocks, meeting up with a fairly substantial bass bar. So it means that the bass bar is fairly tied to the overall body. So this is an area that I think would be very fruitful for more study. Is the bass bar and the effect on high frequency, and other people, Nigel Harris, I think, has talked about end-to-end flexation of the instrument is also activating the instrument, not just the in-plane. I think there's a lot more going on than we have studied so far, especially in high frequency.
All right. Okay. The very last formal question. Okay. We're going to Jim.
Oh, yes. Well, regarding the end of the bass bar, I have noticed a lot of instruments where, because the arching tends to be quite flat near the lower end of the bass bar, and people have this practice that I disapprove of, springing the bar, it doesn't raise the middle, it pulls the lower end down. So you see in many instruments a dip down. When I fit a new bass bar in such instruments, I actually put a little crossways brace under the lower end of the bass bar to tie it into a lot more wood down there. And I'm simultaneously taking out some of that dip that the sprung bar put in there, and I'm making it, I think, the bass bar effectively enormously stiffer because it's tying it into much more of the top.
I think that's a great idea. I have tried similar things, probably not as substantially as you. So for sure, you're getting a much wider purchase without having to make things that much stronger. So I think it makes a lot of sense. Just a comment about bass bar tension is that it's a big topic, but the way I learned and the way I I use less than I used to, but whatever tension I put in a bar is only in, the way I learned is we divide the bar into quarters, and we put absolutely no tension in the outer quarter. So all the tension is in the middle half of the bar, if you will. So that, and you can sort of see when you lay the plate down after the bar is glued, if it had a lot of tension on the ends, the plate will be sitting like this, all sprung up. But if you've done it right, it still sits pretty flat because you've just flexed the arch up in the center. And you can do that very selectively. When I worked with Becker, he would like analyze the arch, and he might choose to actually put some tension in a very specific spot to push up a little hole.
I can see you could push up a little hole, but generally if you make it the bar more curved than the top, the bar, because of the shape you're going to make it, is extremely stiff in the middle. And remember, the stiffness is the cube of that cross-sectional height. You're not going to be pushing that middle up. You're pulling the ends down. It doesn't affect the upper end so much because the arching is much more there. You know, it's narrower and it's a rounder arching, but the arching tends to be quite flat towards the lower end of the bar, and all it does is it makes a big dip there.
It's certainly something to be careful of, that's for sure.
All right, so Sam, do you have any last words?
Well, I'm sorry I dumped so much stuff on you. I should have left more time for, I just wanted to get it all out there. If any of you have reflections on anything we discussed today, please, please feel free to get in touch.